In today's video, we are going to be looking at the photoelectric effect. So if we remember this experiment that we have here, by Hertz, we would get electricity which created an electromagnetic waves that would go and spark over here. This helped prove that, well, light and electromagnetic radiation was a wave. Now, it appeared to work best, this experiment, when the globes were very well polished. But in fact, after more experimentation, he found out that this did not matter at all whether it was polished or unpolished. What mattered more was the wavelength or frequency of the original signal transmitted. So this eventually was the end of Hertz. He figured his experiment did nothing really to improve his quality of life. But Einstein saw this result, and this dramatically changed Einstein's life, as this was where he would win his Nobel Prize, would be in something called the photoelectric effect, which would now be born as a result of him. So looking at that experiment, the main question that Einstein looked at and tried to figure out is, and which led to the photoelectric effect, is how could light waves cause metal to emit electrons? Because essentially that's what's happening. The wave was going all the way from one side of the experiment to the other part and caused a shock, an electron to be released. And why does it only work sometimes? These were key questions that Einstein would look at and try and solve. So let's look at it this way for this question. Sometimes when light was emitted, we would get a free electron over here. An electron would be released. Sometimes when light's emitted, nothing would happen. Now, what makes this even more exciting is that it didn't matter. Sometimes we could put lots of light intensity here, just constant bombardment of light intensity, and nothing would emit. But then sometimes we just put the smallest slight bit of intensity and an electron is emitted. But that kind of goes against this wave idea even more. How could there be just a little bit of light and an electron's emitted, where if we shine light on it with many, many lights on it, and nothing is emitted? Well, along came Einstein. So Einstein's idea about the photoelectric effect shed up quite a bit of light on this situation here. But it also created some more confusion. Is light actually a particle or a wave? We already had black body radiation that started to point towards light being more a particle. It's like quantized. And well, he's going to continue with Planck's idea here to help us solve this riddle. Why, with some electromagnetic radiation, is an electron emitted from metals, while with others, none? So here's what he did. First, he had a lamp, and he shone it through a little hole, and then he used a prism. Okay? Now, if we remember through refraction, the light will refract here at different, so we get different wavelengths coming off of the prism. And then he would decide which wavelength to choose. Now, once he chooses which wavelength, he puts a thin piece of metal there and observes what happens. And he noticed for some wavelengths, an electron's emitted. And yet for others, an electron is not. But he also noticed the electron is emitted instantaneously. Well, that's the photoelectric effect. We make moving electrons from light. Photo, light, electric, electrons. We can make current from light. This is the whole idea of solar power. So what was found is blue light with copper metals made electrons. Blue light with zinc metals made electrons. Blue light with gold metal made no electrons. Well, if that's true, there must be a lot more to the story. So let's consider some of these here. First of all, zinc metal, light comes in with 100 joules of energy. It's found that the electrons emitted have 98 joules. Where did the other 2 joules go? Well, let's take a look here. Metal is gold. Light comes in at 100 joules of energy. It is found that the electrons are emitted with only 90 joules of energy. What happened to the remaining 10 joules of energy? Does anyone have any ideas? Wow. Now, knowing what we have just talked about, I want you with your partner to discuss this image. So here we have infrared light and no particles are emitted. Here I have red light, no particles are emitted. Here I have blue light and I have low speed particles emitted. Here I have ultraviolet light and high speed particles are emitted. Now here's the interesting thing. I could have a lot of infrared light, extreme intensity of infrared light. Doesn't matter what the intensity is, no particles are emitted. I could barely have any ultraviolet light, but yet particles will be emitted. Why is this? Why is this so important? I want you to discuss the significance by using this here and what you have just learned and combine them together. So pause your video and discuss. So now that you guys have thought of and pondered this photoelectric effect, we're going to look at something called the work function and threshold frequency, which helps explain and clear up everything that we have learned so far. So basically, different metals have different threshold frequencies which allow an electron to be emitted, or they have something called a work function. So here is the work function, or the amount of energy needed for an electron to be emitted for each of these metals. As we can see, every metal is slightly different. Now, here's a classic little graph here. We have 3 different metals with 3 different work functions. And here's the frequency, and after this, higher than this frequency is when an electron's emitted. How does that work? Well, this is kind of what Einstein looked at. So if we remember, Planck's constant is right here, multiplied by the frequency of the light, well, that is the energy, minus the work function, the amount of work it takes to eject that electron, and that is what's going to give us my total kinetic energy of the electron. And that explains why there's that little bit of a gap of difference in the energy of the wave coming in and the energy of the electron coming out. It has to deal with this work function of each metal in order for an electron to be emitted. It needs to reach that threshold of the frequency, must reach that threshold in order to emit an electron. So, here's basically what this is. We have my kinetic energy is the photoelectron. What is that? That's the electron that's emitted from a photon of light hitting the metal. The frequency here is the energy of the incoming light. So Planck's constant, remember we learned that lights are quantized, so Planck's constant times the frequency gives me my energy. And then we must minus this work function, which is the work function specifically to the metal. And that's what allows us to now start exploring some classical questions. So now let's get to some examples here. My first example is, what is the energy of a photon that has a wavelength of 4.6 times 10 to the 2 nanometers? Well, first of all, I have to convert this, my wavelength, into meters. So this is going to be 4.6 times 10 to the negative 7 meters. Now, what we're trying to figure out is my energy. Well, we know energy is equal to my Planck's constant multiplied by my frequency. But we don't know the frequency. But I also know that frequency is equal to the speed of light divided by wavelength. So I could put this part here for my frequency. So I'm going to substitute that in. So I'm going to get energy is equal to Planck's constant multiplied by the speed of light divided by my wavelength, which is going to be equal to Planck's constant is 6.63 times 10 to the negative 34 joules seconds multiplied by 3 times 10 to the 8, and that's meters per second. And that's all going to be divided by, we got 4.6 times 10 to the negative 7 meters. So now we do my unit cancellation, and I know I'm going to be left with my answer will just be in joules. And when I calculate that on a calculator, I'm going to end up getting 4.32 times 10 to the negative 19. So we get 4.32 times 10 to the negative 19 joules. Now let's look at my second example. In this one here, we have an experiment that shows the work function for cesium metal is 2.1 electron volts. Determine the threshold frequency and wavelength for the photons capable of producing a photoemission for cesium. So I'll look at what's given here. We have 2.1 electron volts, and we look at what we're trying to figure out is my threshold frequency and wavelength. But to start off here, my work is in electron volts, and we have to convert that to joules. So I'm going to go 2.1 electron volts, and we're going to multiply that by 1.6 times 10 to the negative 19, and that's going to be joules per electron volt, which will end up giving me a total of 3.6 or 3.36 times 10 to the negative 19 joules. So now let's look at our equation here. And my formula is work is equal to Planck's constant multiplied by my frequency threshold. And that is one of the things we're trying to figure out here, which is my frequency threshold. So let's isolate for my frequency threshold here. So we have frequency threshold is equal to work divided by Planck's constant. So this is going to end up giving me a total of, once I plug this in, it's going to end up giving me 5.07 times 10 to the 19, or times 10 to the 14 hertz. Now, we also want to find my wavelength for part 2. So here, we found my frequency threshold. Now, my wavelength, if you remember, the speed of light is equal to my wavelength multiplied by my frequency. So my wavelength is going to be equal to my speed of light divided by my frequency. So we know what my frequency threshold is, so we could find the wavelength of that particular electromagnetic radiation. And after I plug this in using this equation, my frequency right there and the speed of light, so we get 3 times 10 to the 8 meters per second, and we're going to divide that by 5.07 times 10 to the 14, and that's going to be hertz, and that will end up giving me 5.91 times 10 to the negative 7 meters. So then we ended up finding out my wavelength. Here are 2 questions for you guys to pause the video and see if you understand how to do these style of calculations. These here are the answers for these 2 questions. Now here's our last style of question that we're going to be looking at for today. It says, determine the maximum speed of electrons emitted from an aluminum surface if the surface is illuminated with 125 nanometer ultraviolet light. So let's look at what we know here first. First, we know my work function of aluminum, according to this table, is 4.08 electron volts. Now, I have to convert that to joules because we tend to work in joules here. So I'm going to times that by 1.6 times 10 to the negative 19 joules per electron volts. This is going to end up giving me 6.5 times 10 to the negative 19 joules. Now, I also know here what is my wavelength. So my wavelength is equal to 1.25 times 10 to the negative 7 meters. Because remember, we have to convert that to meters. What we're trying to figure out is my velocity of the electron. Now, in order to figure out the velocity of the electron, we must first figure out what is the kinetic energy of this photon being released. So then we must use our formula. The kinetic energy of my electron is going to be equal to the energy of my photon, which is Planck's constant, multiplied by my frequency of the ultraviolet light, minus my work function, or of the aluminum. But we only know my wavelength. So for this, we're going to have to put in speed divided by wavelength, which is equal to frequency. So we're going to have Planck's constant multiplied by the speed of light divided by frequency, subtract my work function. Well, let's plug this in here. We're going to get 6.63 times 10 to the negative 34 multiplied by 3 times 10 to the 8. And that's all going to be divided by, my frequency is, oopsie, that should be lambda, not frequency. My wavelength is 1.25 times 10 to the negative 7. And this is all going to be subtracted by 6.5 times 10 to the negative 19. Now when I calculate all this, I'm going to end up getting 9.38 joules, or times 10 to the negative 19 joules. All right? Well, now we know what my kinetic energy is. Now we can figure out what is my velocity, because we know kinetic energy is equal to 1 over 2 and mass times velocity squared. So the velocity is going to be equal to 2 times my kinetic energy divided by my mass, and we have to square root that, which is going to give me 2 multiplied by 9.38 times 10 to the negative 19 joules, all divided by my mass, which is 9.11 times 10 to the negative 31 kilograms. And we want to square root that, which will end up giving me a total of 1.44 times 10 to the 6 meters per second. So here are the last 2 questions for you guys to try, or 3 questions for you guys to try and see if you understand what is happening here. These are the answers to those questions.